Hi there, I saw this baby on eBay and could not resist. It was described as for parts not working. Verbally the owner said that as far as he remembers one of the channels was working, sort of, but no idea which. This is a Kingshill V series dual power supply, actually two identical units in one big enclosure. Each of the units is good for up to 150 volts. I don't need voltages of 100 volts or more often, but it's nice to have the capability. That is, of course, if I can get this unit working. It wasn't used for quite some time and stored in a garage, so before trying it out I want to open it and check for obvious problems. The rear confirms that these are two identical but separate units, each with their own serial number. The model is a T15A03C and should be able to produce 0 to 150 volts, 0 to 0.3 amps, which when multiplied gives 45 watts as stated. The input is specified as 240 volts, 0.3 amps, 45 to 400 Hz with a slow fuse of 1 amp. As it's common, no fuse on the output, instead the current limiting function is used to protect the power supply from overload. So far so good. Let's have a closer look inside. There are a total of 8 screws, 4 in the feet and 4 in between that need to be removed. When that is done, the two power supplies can be slid out. They are still screwed together, so they come out as one. The whole thing is quite heavy and pretty dirty. Because it's two identical units, everything you see is times 2, but I'm just describing one unit. At the back is the power transformer with a PCB on top for the connections. In the middle we have two sets of heat sinks with the power transistors on them and some resistors and caps wired to them. In the front is the PCB containing the actual control circuit. For some strange reason the PCB on the right unit is mounted further back than the one on the left. A closer look at the PCB on the right side unit. Wow, just look how scorched that PCB is under these diodes. This looks more like a major disaster happened here, and the diodes are probably new ones replacing those that went up in flames. The rest looks pretty original. The op amp is a good old 741, maybe the 99124 is the date code and points to 1999. I don't see any leaks and bulges on the caps. The left side PCB looks very similar, although part of it is hidden under the front bezel. It has the same disaster area on the left. Lots of dirt and gunk lying on the PCBs. These need a clean before any attempts of powering them up. The mains transformer has a PCB on top for all the winding tabs and connecting wires. More importantly, around that yellow capacitor are 4 diodes. This is actually the full bridge rectifier for the output, and the red and black wire carry the DC to the rest of the circuit. There is a second independent tab closer to the camera marked as 35 volts AC for powering the control circuit. It is rectified with a single diode, and the blue-red and white-black wires carry this DC. Here's a side view showing some of the power transistors. Each unit has 2 heatsinks and each heatsink has 2 TO3 power transistors. I started cleaning the power supply, and here's a view of the underside. Each unit has a large blue smoothing cap mounted horizontally below the transformer, and there is another not quite as large blue cap behind the front panel. Turning the unit upside down allows a better view of the lower part of the front panel. Notice the 2 fat red wires. These connect the sense terminals to the output terminals. Although the unit supports 4-wire mode, it is shipped with these links in place. To use the 4-wire mode they have to be removed or cut, and from then on you must provide your own links on the outside when not using 4-wire mode. Since the maximum current is just 0.3 amps, I don't think it makes sense to enable 4-wire mode, so I leave the internal links in place. And here's a view of the analog instrument from the rear. It has a very elaborate combination of shunt resistors made of resistive wire to support 2 voltage ranges and 1 current range. After the clean and no obvious issues found, it's time to try powering the units, starting with the left one. Not visible, but power comes through my current limiting light bulb system. It is essential when powering suspect units. I leave a link if you have not seen how I build it. The multimeter is measuring the output voltage. The power switch seems to be stuck. With quite some effort I finally manage pushing it, but nothing happens. Nothing when I move the controls. This unit seems to be completely dead. Let's try the right unit. Its power switch goes a little bit easier and its neon lights up green. And the analog meter shows a deflection. Turning the voltage knob increases the voltage, but nothing on the digital multimeter. Oh, hang on, of course it's still connected to the left unit. Now we're talking. And it follows when I move the voltage knob. The right unit seems a lot healthier than the left, but the fact that not even the left neon lights up points to a problem with mains. I connected the multimeter to the primary winding of the left transformer and, after struggling with the power switch again, nothing. There is no mains voltage reaching the left transformer. Maybe a fuse is blown? There is a fuse holder just above the power switch. But testing the fuse for continuity shows that it's fine, so I put it back in. The power switches are of the double pole single throw type, and connecting one lead of the multimeter to neutral, I can verify that on the working power supply, neutral reaches the transformer when the switch is turned on. On the left unit it does not. I searched the wiring for problems, but to cut a long story short, it turns out that the problem fixed itself. Suddenly power did get through and the switch turned a lot easier. I suspect the contacts were tarnished from not being used for ages, and my repeated switching during the troubleshooting solved the problem. There are a number of generic manuals and schematics of the Kingshill V series out there. This here is the one that most closely resembles what I have. I say closely because there are still significant differences. For example, there's just one series transistor here, and I have 4. The manual just states that VT6 may consist of 1 or more power transistors. Another example, it shows a bridge rectifier and identifies it as MR2, but we know that these are actually 4 discrete diodes plus a small capacitor on the transformer. Most frustrating is that on those manuals that actually list component values, they are often generic. For example, C2 is just listed as, quote, reservoir capacitor. No capacitance or voltage rating. Same for C5, which is just, quote, output capacitor. I get that Kingshill saved money by just using the same manual for a whole series of power supplies with voltages of up to 150 volts and currents up to 10 amps, but it's really not very helpful if you have a burnt component and no idea what it should be. I hope in my case, with 2 identical units, a bad component may still be identifiable in one unit, but as we have already seen, it appears that both units suffered the same disaster some time ago. While we're at it, it appears that the whole set of 3 Z diodes in series is marked as MR13 and unlisted in any component list I found. And MR13 is on the schematic, but that is a single normal diode, and 1N4005 by the looks of it, and across the output capacitor. So clearly not 3 Z diodes in series. An incomplete and slightly wrong schematic is still better than no schematic. In trying to make the best of it, I spent some time reverse engineering what replaces the single VT6 power transistor on the schematic. It's all that stuff mounted on the 2 heatsinks. The whole assembly connects by wires to items on the front panel and the PCB, and I have not all traced it out yet, but the principle is clear enough. Basically, it's 4 high voltage power transistors of type 2N5240, all wired in parallel. For 0.3 amp maximum current, the whole thing seems totally over-engineered. After getting an idea on the power transistors, I tried to find out what the reservoir capacitors should be. The easiest accessible one has the crucial data hidden by the mounting clamp. No choice but loosen the clamp temporarily to allow sliding the cap despite it being held by that green resistor. Excellent, it's made by Sprague, which means it's probably still good. And its data states 680 microfarad, 250 volts, 85 degrees Celsius. It measures 652 microfarad and an ESR of 0.24 ohms. 4% low, but for caps that's still good. And its twin in the other unit measures 637 microfarad with an ESR of 0.21 ohm. 6% low, but still okay. The output caps can be read directly, 150 microfarads and 250 volts. It measures 156 microfarad with an ESR of 0.28 ohm, still okay, and its twin in the other unit reads 164 microfarad and 0.26 ohms. Because of the diode across the caps, I repeated the test with the Finersi LCR STA1 set to 0.3 volts and it confirmed the measurements. Another mystery cap is this orange one fixed to one of the heat sinks of all places. In circuit it reads a very unlikely value of nearly 49,000 microfarad. And its twin shows nearly the same nonsense. To get correct values I have to desolder one leg and repeat the measurement. Okay, 33 microfarad and 0.52 ohm make more sense. And after losing its bracket and sliding it out, its nominal value of 33 microfarad 160 volts means this one is still good, and the same is true for its twin. The left unit's PCB is half hidden under the front bezel, making measurements difficult, but since there are already additional holes in the PCB, I decided to move it back to the same position as the right PCB. Let's do some more tests of the electrolytic caps. C1, the large one on the left PCB, measures 146 microfarad with 0.32 ohm ESR. It's marked as 150 microfarad 63 volts, so that's okay. Its twin capacitor has almost identical values, so these caps are both okay. Next comes C6, which should be a 100 microfarad 10 volt cap. It measures nothing. This normally means a bad cap, but since I'm measuring in circuit, let's see if its twin says the same. That produces a reading, but just 31 microfarad with a pretty high ESR. These two caps have to be replaced for sure. Next is C3, a 4.7 microfarad cap at 160 volts. It measures 5.48 microfarad and 2.1 ohm ESR. More capacitance than normal is a bit suspicious. I don't have a replacement, so I leave it for now, but it's a candidate for replacement. Its twin measures 5.58 microfarad and 1 ohm, same story. Since I'm replacing C6 on both, I have a good look at the PCB undersides and the obvious repair that was done. It's quite a show. I would have tried to grind away the charred surface because that carbon may be conductive, but it seems the unit was working after that repair, so let's hope it continues to do so. I did not have a suitable axial replacement, so I pressed capacitors with radial leads into service here. Not pretty, but it will do. The same repairs on the other unit. The PCBs are very close to the lid, so there is no room for any standing capacitors. Testing the left unit with a 400 ohm load resistor. About 62 volts on the multimeter and the analog instrument shows around 160 milliamp, which, given the accuracy of the meter and resistor, is probably okay. Switching the analog meter to volts and it shows slightly more than 60 volts, so that's working. I can increase the voltage, but at about 68 volts it doesn't increase anymore as the unit is now limiting the current. Sadly, there isn't an indicator that the unit is now in constant current instead of constant voltage mode. I can reduce the voltage so the unit goes back to constant voltage mode. When I remove the load, I can now increase the voltage to the maximum as the tiny current to the multimeter is way below the set current limit. But there's still a problem. Let me demonstrate. There is no load connected, just the multimeter. I can increase the voltage to the maximum using the coarse voltage control, and using the fine voltage control to get it to the last few volts. Then turning it back down to practical 0. If I now turn the current limit between min and max, nothing changes. This is the correct behavior. Now I repeat this on the right unit. Voltage control allows full voltage, back to practical 0. But when I now turn the current limit from the lowest to the maximum, I get almost 40 volts on the output. Definitely not correct. After testing diodes with a multimeter and then transistor junctions, I quickly found that VT5, a BC108 NPN transistor, had given up the ghost. I replaced it with a BC107 I had. It's the shiny transistor closest to the camera. I even added the plastic spacers from the old one. That fixed the problem in the right unit. All working, I thought, somewhat prematurely, because shortly afterwards the left unit shows exactly the same fault, and, no surprise, its VT5 has failed as well. After replacing both units are now working. I'm just wondering if this was just happening after a long time of no operation, or if it indicates another problem somewhere. I guess time will tell. I tested the two C6 caps after removing them. The first one still says open circuit or low capacitance. The second one still shows about 30 microfarads, which is too low for a 100 microfarad cap. One of the two transistors showed a single diode in the component tester, and the other two diodes and a resistor. Anyway, time to move to another annoyance. The line cord is less than half a meter long. I considered replacing it with a longer one, but then I decided to simply take it away completely and add an IEC C14 socket. That requires removing 4 screws that hold the two units together. This is needed to get to screws that hold the back panel on the left unit. That unit has the line cord going in, and at the front is a short piece that extends the incoming mains to the power switch of the right unit. With the panel removed, I can take off the UK power plug and then pull the line cord through until the panel is free. While the rubber cable guide looked okay, I noticed that there wasn't any sort of strain relief. A hard yank on the line cord would have ripped the connection of the mains power switch. I can't imagine that it left a factory like this, more likely some modification from a previous owner. I cut the hole for the IC connector and stupidly drilled a hole at a completely wrong place. This means I now had to close two holes, one where the original line cord came in and one that was my mistake. I used black plastic pieces glued in place to cover the holes. The shortened line cord is now terminated on the IEC socket and the rear panel can be installed again. Here it is with the panel back in place and the two units tied back together with 4 screws. The power supply was upside down for this shot. I was somewhat concerned about the large burn mark on the PCB, but as this thermal image shows, this area is fine. What is a bit concerning is this 9V Z diode MR5, which sits at 105 degrees Celsius. This, together with the larger transistor, forms the power supply for the PCB, and that means it runs that hot whether you draw current from the output or not. I'm considering buying some 9V Zeniths rated 5 watts. My idea is to mount one of those somewhat elevated from the PCB to improve its cooling and maybe adding a heatsink for the transistor. I want to finish demonstrating how to operate the power supply. I'm just using the right one as the other one works exactly the same. In this setup, the red multimeter shows the voltage and the yellow the current. You can select the voltage with the left knob, which is for coarse voltage selection. There's a fine voltage adjust, which is the most right knob and has something like a 2V range. If I push the momentary switch next to the power switch to the volts times 2 position, the analog meter shows double the deflection. It does not change the output voltage. The idea is that it helps to set very low voltages, like here when I'm trying to set 10 volts. In times 2, that would be the second major tick mark on the upper scale, or 20 volts. Okay, it kind of works reasonably well within the limitation of the analog instruments. One way to set a current limit is to first crank up the output voltage, because if the voltage is too low, you can't adjust the current. Then you push the momentary switch down to set the current limit position and hold it. This kind of shortens the output internally. Now the analog meter can be set to show the current, and the value can be set with the middle knob. It's kind of crazy that they use a 1 amp meter for a maximum current of 1/3, making fine adjustments pretty much guesswork. I can now add a load, in this case 100 ohms. And as I increase the output voltage, the current increases as well until we reach a limit of about 200 milliamps. Further increasing the voltage has no effect on the output because we are now in constant current mode. A quick sanity check. We have a maximum voltage of 20.8 volts and 199 milliamps. If you divide volts by current, we get about 104 ohms, which is within tolerances of my load resistor. Switching the analog meter to current confirms that it had reached the preset limit. Unplugging the load, and now the voltage is no longer restricted and jumps to whatever values I had increased it to. This can be, of course, quite dangerous for a connected device when its current drops, so one should not mindlessly increase the voltage when the unit is in constant current mode. The better way to do this is first to adjust the proper voltage for the device under test while it's not connected. Here I'm using 6 volts, which is hopeless using the analog instrument, but no problem with a digital multimeter connected. Then, with the device still not connected, holding down the set current limit and adjusting a suitable limit on the analog instrument set to read current, for example 100 milliamps. I can now connect the device, in this case a 20 ohm resistor, and as expected the voltage collapses because the current limit is exceeded. But if the device is, say, repaired and now draws much less, simulated by the 80 ohm resistor, the 6 volts is maintained because 73 milliamps of current is below the limit. Under all circumstances, the voltage never exceeded 6 volts safe operating voltage set at the beginning. You may have wondered that in all the scenarios the middle switch was always in constant voltage mode and not in constant current. The manual says that while the constant current achievable by using constant voltage with current limit functions has a short-term stability of better than 1%, the constant current mode is much better. That may be so, but it's bloody scary and I can't see me using it much. Let me demonstrate. The voltage control is almost down to 0 and the load consists of a 10 ohm in parallel with an 80 ohm resistor in parallel with a 1K, so about 8.9 ohms in total. The first two are power resistors, the 1K is not. The unit is in constant voltage mode, but now I set it to constant current and adjust the current to 100 milliamps. Setting the analog meter to volts, it doesn't show much because it's just about 0.9 volt on a digital meter, which makes sense. With zero tolerance resistor, 0.89 ohms times 100 milliamps should be 0.89 volts. If I unplug the 10 ohm resistor, only the 80 ohm and 1K resistor remain as load. And the power supply adjusts to maintain 100 milliamps by raising the voltage to almost 8 volts. Now I unplug the 80 ohms. The voltage shoots up to almost 100 volt in trying to keep a 100 milliamp current. That is 10 watts, and the poor quarter watt resistor has no chance. Once it has released the magic smoke and become open circuit, the power supply raises its voltage even further. In its attempt to maintain 100 milliamps even with no load, the power supply throws everything it has at the output, 187 volts. Talk about scary. While the smoke clears, I'm considering replacing some parts to reduce the heat in the PCB, but I haven't decided yet. If so, I may do a part 2. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.